If anybody else wants to record or be a co-host, just let me know. And it helps me if you turn on your cameras. If you don't want to, I understand. You don't have to. It just helps me really. And I don't really care if you're eating. If somebody does, then they can look away. Or just turn that off. Okay, now getting back to the problems. Before I do anything more, I want to do a problem that I think is representative, in my opinion, of the types of problems that you could get in power. It's with mixing delta and Y. Now, I got to tell you one other thing too. With delta Y configuration of systems, I'm going to go through this for a very important reason. People mess up delta and Y often by the transforms. Where you take, I always tell you this, and I'll say it again, we always do everything in the Y configuration, and then we get whatever information they want. You will not go wrong doing it that way. Does everybody hear me? Always transform. If it's a delta load, transform it into a Y load. If it's a delta source, transform it into a Y source. And a delta source is usually referenced as line to line or line voltages, VAB. You follow me on that? If it's VAN, it's phase voltages. Now, that said, this problem, unfortunately, it's a little inked up in this book, is problem 5, where is that? 0.54. It's this problem. Can you all see this? Guys, it's inked up, but can you see it? Can you make it out? I've got another book with this in it. Hold on for 1 second. This one I won't ink up. This is my copy. This is slightly different than that, but it has this kind of a problem. Looks like I've inked this book up too. Hold on for 1 second. Oh my gosh. All right. With this book, I mean, in this book. Now, everybody can see this, right? If you got that, if you don't understand this, listen carefully. I look at this configuration. Everybody sees there's a common point on all these sources. Can you make that out? That immediate tells me immediately it is a Y configured source. Everybody got that? So the source is Y. Now, when I look at the load, first thing I notice is the loads aren't connected at a single point. This load has, I mean, if you look at this, all these loads aren't connected at a single point. You can pick any point, say B. Well, B is not connecting this load, is it, class? So you can see it's a delta load. Are you with me? And pretty much if you go between A and B, this is capital A, capital B, you can see that's where the load is. There's not a neutral between it. So what I recommend you do, when you recognize the configuration, you put Y delta right here. Now, the only thing you do is one phase. You do the A phase. When you do the analysis, and really you can put A capital A if you want, but it's the A to neutral phase. So do we have VAN? Anybody can answer that. It's rhetorical. But if you look at this, do we have VAN just by looking at this? Anyway. Yeah, we do, because what? Even though this is a little inked up, but that is a common point between all these sources. Therefore, it is the neutral. Do you see it?
Yeah.
Can you all see this, by the way? I just need to know that you can see what I have here on the screen. On my screen, it's clear, but I don't know if it's clear on yours or not. Is it? Okay, so there's a neutral here. That means I have VAN at 120 at 0 degrees. And that's RMS. After that, next thing I'm going to do is find the line impedance. The line impedance will be the same for delta or Y, and it's 0.6 plus J 0.4, right? By looking, class, do y'all see that? It's a little, there's a little glare. With me? Okay, thank you. Okay, 0.6 plus j.4. I'm going to start drawing this. So it's plus the minus VAN is 120 at an angle of 0 degrees, and that's volts RMS. Then I put the line impedance 0.6. And I have a reactance here of J 0.4. The units of that are ohms. This is small a. This is small n. We ground that. This is capital A. This is where the load is. And here, I'm just going to say this. You'll notice the delta load is 24 plus J18, correct? Yeah. Can everybody see that? It's a delta load. So we have Z delta equals 24 plus J18. But we want ZY. So ZY would be what? Anyone? At all. You can turn on your mics, might as well.
What? So 6 plus, or 8 plus J6?
But what are you doing? You're dividing Z delta by 3, right?
Yes.
That's the first thing I want. So it's Z delta by 3, which would be 8 plus J6 ohms. So I go ahead and put this load here, and I'm just going to write 8 plus J6 ohms here. And this is capital N, and then I'm going to ground this. Are you with me?
So if we wanted to, we can make them both Z delta instead of ZY, right?
Yeah, but if you're going to make them, you're going to have to, if he makes this point, he says, can I make them both Z delta? Here's the point when we do Z delta. Just listen now. When we do Z delta, we're going to have a load here that's going to be magnified by 3. And we're also going to have another load. Let me see if I can show you this. Yeah. I want to show you it here. All right. This one right here, I'm going to come back to the problem and finish it. But here, do you all see we have a delta source and a Y load? Can everybody see that? We've got a delta source and a Y load. The Y, there's a connection point there. Well, if we look at this, if we had a delta load, it would be between here and here, right? You all see that?
Yeah.
All right, now look, if you do it that way, look at the line impedance you've got. You got a line impedance there. Then you would go through the delta load, right, to this point, right? And then when you get to this point, you're coming back through the line impedance. Now, it gets more complicated if you do it that way. That's my statement. Who asked this question, by the way?
That was me.
See, if you have no line impedance, you can do delta delta easily. But the minute you have line impedance, things get complicated quickly, all right? So my advice is to stay away from it. Is that fair? Okay. Let me get back to the problem. That's ZY. So now this is the equivalent YY. Y'all agree with that? Y source, Y load, right? Now what they ask for, they just want, oh, wait a second. For this one, there's actually 2 loads. Pardon me. My bad. If you look here, this is a delta load, right? Can you
out of frame
about that? Yeah, I'm out of frame. Bear with me on this one. I was trying to just do this problem for starters without this extra load. I converted that load right here to a Y load. Do you agree with that, everyone? First, let me just make sure everybody agrees with that point.
Yeah.
Yes.
I mean, nodding the heads is fine. Thumb, any kind of agreement. I got 1, 2, 3. Kaylin, do you got it? And Connor, I mean, thank you. I just need a little affirmation so I can continue. Well, if you see that we've got delta Y, at this point, do you see you could easily calculate this current? Let's just work this problem. Agreed?
All right.
All right, and what would that current be through here? Call it IAN. If we just, this was the problem. Can you all see IAN would be, that current right here is this current, isn't it? Isn't that current IAN flowing here, that current I line, right? And IAN would be gotten by taking 120 at an angle of 0 degrees and dividing it by the sum of these 2 impedances because they're in series. 8.6 plus J 6.4. Now, we don't care about that right now, but do you all agree with that?
Yeah.
Now, if I have that current right here, and the load was delta, I want you to listen to me. The delta current will have a square root, you have to take the magnitude of this current and divide it by a square root of 3. I'm going to go through this again. If this is a Y configured current, if I want YAB, can somebody just give me the magnitude of that in angle? If you want, I'll do it with octave, but I'm trying to focus on my delivery right here. Anybody got it? Just for this, 120 over 8.6 plus J 6.4. I just need the magnitude and angle.
Uh, 11.194 at an angle of negative 36.66 degrees.
At an angle, say that again.
Negative 36.66.
I'm going to leave it at that, okay? 11.194 at minus 36.6 degrees. You can check, see if that's correct. Anybody else confirm that? Anybody at all? Thank you.
Yes.
If that's it and I want IAB, now that is the current in the delta load. All right, if this was capital A and this was capital B, our delta load would be 24 plus J18. Right? I'm just taking this out right off the picture. This current here would be I, capital A, capital B. What you would do is take the magnitude of this and divide it by square root of 3. So it would be 11.194 divided by square root of 3. Then the angle you would add 30 degrees to. Remember, anytime you go from Y to delta, you increase the angle by 30 degrees. If it's current, you decrease by the square root of 3 the magnitude. If it is voltage, it increases by the square root of 3. So this would be the magnitude, and the angle would be minus 36.6 degrees plus 30 degrees. If you want to give me that, it's fine, but you don't have to. You can see this is about minus 6.6 degrees, right? And the magnitude is, I don't know, is it 7? Something like that? Doesn't really matter. You all follow me? How many understand what I've done there?
Mhm.
Okay,
It's,
if you want,
6.46.
thank you. 6.46, and the angle is minus 6.6 degrees, about. All right, now that's with one load, right? The actual problem has what? Remember, it's still Z delta, right? Now, please listen, you always go to YY. Take a look at the actual problem had what? It had a second load here. I hope you can see it. I've got that turned up all the way and it's still not that bright. Do you all see there's another load in parallel with this load? You all with me? Now, please be careful on this one. I'm going to see that. This is another load, and the load is between the A and B lines, right? And therefore, it is in parallel with the actual load. Are you with me? Everybody? You
Yeah.
see it?
Mhm.
Okay. Now, look, what configuration is this load, the second load right here that I'm showing you?
I.
It's Y, and obviously what I'm trying to tell you is it's a Y configured load. That's in parallel, right? The Y load is 6 plus J4, right?
Yeah.
All right, now, we're still going to do this in the Y domain. Then we'll go back and get this right here. The actual current they want is this right here. They want the current IAY, so it would be the current literally flowing here, upwards. So you don't need to redraw this, but I'm going to take the 120 volt source. I know it's out of focus. I'm just redrawing the circuit for everybody's benefit. Plus the minus, it's just 120 RMS at 0. Then my line impedance is 0.6, and this is J 0.4. This is the small a, this is the neutral, right? This is the capital A. Now I'm going to put them in both in parallel. The load that was just shown to you was 6 plus J4. and it's in parallel with 8 plus J6. The actual problem asks for this current. Yeah, IAY is this. IAY is this. So it's the current plus through the load 6 plus J4. Now you can do this in a variety of methods. Let me just explain a couple. You all see what you can do is get an equivalent source right here, or equivalent load, pardon me, right? Do you all see that these two are in parallel, class? How many do? If they're in parallel, we get equivalent load, then we could use voltage division to get the voltage between VA and N, right? Agreed. With me? Now, once we had the voltage between this terminal and this, we could easily get it, and I'm going to do it that way. We could get the current here by taking the voltage divided by 6 plus J4. Do you agree with that? That's one method. A second method would be find the total current flowing here, and I'll call that I line right there. And then using current division to find small a and capital, or small a, small y, the current through here. You could do that using current division. I prefer to find the voltage here because it's more telling if I have the correct answer. This should be less than 120's magnitude. And then simply dividing it by 6 plus J4 to get the current. Okay? So what is the equivalent load of these two? How would you do it? Anyone? You can just tell me.
On the inverse.
What would we do? If this is really like what? Z1, and this is like Z2, isn't it?
Yeah.
Y'all agree that the first load, second load looks like Z1 and Z2, class? Right? How would you get an equivalent? You could say Z equivalent to this would be Z1, Z2 over Z1 plus Z2. How many agree with that? They're in parallel. Do you all agree with that or not? Thank you. Thank you. The more information I get from you, the better it is for me and the better I can help you. Well, I can do that. Can anybody do that for me? And I'll take it in rectangular. I'm going to draw the final circuit. So then we have plus to minus 120 at 0 degrees. We have 0.6, J 0.4, and then we have an equivalent load, and anybody can give that to me.
So 48 plus 24J over.
No, I need the real part and then the imaginary part. I know how to do the equation. Anybody?
I got a 3.43 plus 2.4J.
Say it again.
I got the same thing also.
Say that again, please.
3.43 plus 2.4J.
2.4?
2.41.
Well, all right, that's close enough. That's capital A, that's capital N. And you realize that small a, small n, these are effectively ground. So if we want to get the voltage VAN, right? Do you all agree we can use voltage division to get this voltage? Everybody? Right? We've got a voltage, we have two series impedances, right? So we can say that V capital A N is equal to the source voltage 120. It's at 0 degrees, so I'm not even going to put it there. And it's times the load we want the voltage across, which is this 3.43 plus J 2.41. And then it's divided by the sum of these two, which would be what? That would be 4. 03, is that right? Plus J 2.81, right? This is 4.03 plus J 2.81. The only thing I did is add this plus this. That would be the actual voltage VAN. Do you agree with that, class? Ray, yes? Okay, thank you. If you can give me the magnitude and angle, or you can give it to me in real and imaginary, because that's not the final final answer we want. But I want this right now to calculate that. I probably will ask this kind of information. I'll ask for intermediate information. When you get it, let me know. I'll try to get it myself. So I got 102.27 plus J 0.196, and the magnitude of that is 102, about 0.27. And if I take the angle, I get just about 0 degrees.
So I got 102.391 for the magnitude and an angle of 0.205.
I'll show you. You probably got the same thing I got. That's what I got. So my angle is 0.11, and the magnitude is 102.27. I probably rounded up here somewhere. All right, you've got about the same thing, right? Y'all get that, people?
Yeah.
All right. Now that's the voltage. That's the voltage right here, from here to here, right? That voltage is also the voltage across this load, right? Does everybody see that? That's the load where they want the current, isn't it, class? And if you look at the original problem, they want the current flowing. This you probably can't. You can't see it at all. You can't. It's very light, but it's light blue AY. Now you have it in your OneNote. If you print out OneNote, you'll see it. They want this current. Well, that current flows 6 plus JY. It's really one of the Y loads, isn't it, class? You all agree with that? It's the current through the 6 plus J4. To get that, we simply take VAN that we just got to get that current, and I'll put it right here. I small ay would be the voltage we have here, VAN, divided by the impedance 6 plus J4. How many agree with that? I'm doing this methodically for a lot of reasons. Do y'all see that, class? Okay, thank you. Now you can give me that value if you want. It's in the solutions, but it would be, I just take what I got and divide it by 6 plus J4. Let me do it here real quick. So if I wanted that IAY, I would take my VA, oh, it should be capital AN here, it's small, divided by 6 plus J4. That's real and imaginary, and then the magnitude. would be that. And if I take I get the angle of minus 33.58 degrees. So that means that current, does that agree with the book? Can anybody tell me?
I got essentially the same thing when I plugged into my calculator.
I think it agrees with, I'm sure it does, really. Um,
Oracle or Octave is blocking.
I don't know. I'm just copying down, moving it. Thank you. All right, y'all get that? Let's talk about one other one. How about this problem here? This is 555, and I gave you that, didn't I, class? Do y'all remember this is an assigned homework, correct, class?
Yeah.
I mean, it is. Whether you admit it or not, it is. Now, if you look at this, again, make sure you can get this. Source is y, right? Agree? I mean, source is delta, pardon me. Source is delta. That wasn't intention. Do you agree with that, class?
Can you explain that a little more, please?
Sure. You understand what a delta source is, that what? The connections are only between the lines. There's no neutral. You see no neutral here, right? There's no point that connects all three sources. That's the key. If you look here, there's a single point that connects all three sources. That would be a neutral. You all see that, class? Now, here it is a delta. Here it is a y. This is the load. The capital A, capital B, and capital C are the various phases at the load-in. Therefore, it's a delta y. Now, we always transform to yy, correct? I'm going to do this one. I'm going to do a few other things with this one.
I looked up the results and the book solution for the last one. They got a very different answer.
For what?
The 5.54. They got a very different answer than what we got.
If you gave me the right value for the parallel combination of those two, then that should be the right value. But I'll tell you, I'm just going to take a second with this one. This is the key. If that's right, everything else is right. Right here. If this is right, everything else is right. Now, if this times this over this plus this is unequal to that, and I have a feeling it might not be because I'm going to do it right here to see. It may not be. Then everything else falls apart, but that's how you do that. If you take, call it z equals, it's 8.8 plus, pardon me. You can see the screen, right?
Yes.
So it's 8 plus J6. 6 plus divided by the sum of these two, and I'm going to put it down. I got 8 plus 6 plus 1J times quantity 6 plus 4, 10. So what did I do? Pardon me.
So you put an extra asterisk in your,
I did. Why is this thing not working? Oh, that's why. Somebody confirm that this is the right answer right there.
When I did it, that's the answer I got as well.
I appreciate that. That tells me at least it's right. Now let me see where the problem is, if there is a problem.
someone made a very good point that I was misreading the solutions. That's on me. Sorry for derailing.
It's all right. Thank you. Anyway, good to double check. That's the places where I see the big mistakes, is right in the equivalent load. And now getting back to this problem. So thank you. That's right. Back here, for this one, if it's a delta Y configuration, now listen carefully. When we're going to do this, we have to change this load into a Y. Do we all agree with that? Give me a show of hands if you do. All right, so if we change this into a Y, first we have to divide 108 by the square root of 3, right? You agree with that? Square root of 3, and then what do? We subtract 120 degrees. Does everybody agree with that?
Yes.
I'm assuming you do. I really, it's when I have just blank screens and no microphone, I don't know what the majority feels like, but I'm assuming you do. So I'm going to show this as a YY configuration, okay? For the YY configuration of this, I have 208 at 0 degrees reduced by square root of 3 in magnitude and subtracting 30 degrees will give plus or minus 120 at minus 30 degrees. Now you can check that, it'll be about 120. Next, I put in, this is the YY equivalent on problem 555. Now I put in the line impedance just for the A phase. So here I have 0.1. This is problem 555 if you want to look. And it's J 0.1. Then that's small a. That's the neutral, small n. This is the sending end or source. Now we come to the actual load, the thing that's using this power, capital A. And here we have, it's in a Y configuration, so we have 10 plus J4. And then that's capital N and grounded. Now, what's asked for in this problem, but we're going to get many things in this particular problem. They want the magnitude of the currents, IAN, and in the delta source. Now, we're going to go and get the delta currents in a second. We're going to stay in the YY configuration, get everything. The first thing we're going to do is get this. That is I line, which is I capital A capital N. Does everybody agree with that? And that will be I capital A N here will be equal to 120 at an angle of minus 30 degrees. There will be things, points get heavily taken off if you don't have that angle. Just remember, it's very important to be completely accurate. Then it's divided by the sum of the impedances, 10.1, right? And it would be J plus J 4.1. Now that, I'm not going to do this. That's going to give a magnitude and an angle. Do you all agree with that? Right? Can you all hear me okay with
Yes.
this? Magnitude and angle, it's going to give us that. Once we have that, I'm looking at what they want. They want the currents. We've got this, which is the line current. So we've got the line current and we have, now we have the actual load current because the load is in the Y configuration, right? We've got two of the three, but listen, they want I, and they want I, AB. Now, IAB would be at the load end, right? It would be across the delta load. I want you to listen to what I'm saying. Do you agree with me?
Yeah.
Technically, this would be VAB. That would be the delta voltage at the load divided by Z delta, right? Now just listen to me carefully. Well, VAB at the load end here, and I'm going to just prove to you something you're going to use over and over again. That would be equal to the square root of 3 times small VAN in magnitude. Then it would be the angle AN plus angle at capital A, capital N. And this should be capital A, capital N. Let me redo that. IAB would be equal to, don't worry about that, be equal to, I'm going to do this part, square root of 3 in magnitude times V capital A capital N. Angle would be theta AN, whatever that angle was for VAN, plus 30 degrees. That would be VAB divided by Z delta. Now Z delta is 3 times ZY. Does everybody agree with that? This is really VAB divided by Z delta. That's IAB. Y'all agree with me, class? Thank you. Now look here, look what happens. What is this really? Well, you can see I can take square root of 3 and 3 and make that 1 over the square root of 3. Do y'all agree with that? I'm just reducing. Now, when I take VAN over ZY in magnitude, that's the magnitude of what? I capital AN, isn't it? See how I have VAN and ZY? That's the actual what? That's the actual current in the load if it was Y, correct, class? Now the angle is what? It's actually the angle theta AN plus 30 degrees. And what I'm really getting at is this. Whenever you have a Y current and you want the delta current in a load, you simply divide it by square root of 3, the magnitude, and add 30 degrees to it. Got me? Now to get the Y voltage, if there's something interesting in that chat, let me know, because it's really blurred out in mine. I mean, it's overwritten basically. Now, if you want V, he wants the current in the actual source. I'm going back to this. Well, actually, I'm going to show you the picture. The current in the source, if you think about this problem, the current small a, small b would be flowing this way. Really, we're talking about the current from B to A that would be flowing in this circuit, right? Well, that current would be in magnitude this current, the line current divided by the square root of 3, just like the load. Do you agree with that? Right? The line current here is flowing, right? Well, it's going to be this divided by the square root of 3. Here's why. Somebody's going to ask me this. You see there's a current there and the current there. Forget the
Can you lift your
magnitude.
book up just a little?
Thank you. I'm sorry. You see how these two things, this is point A, they want the current just through this one. There's a current here and a current here that are adding to go down here. But the way you get this current, that is a delta current, is you take the magnitude of the line current, divide it by square root of 3, and then add 30 degrees. So I'm going to get it. Now, what did you notice about what I just said, by the way? Well, if I take the magnitude of the line current, isn't this right here the magnitude of the line current, right? I mean, IAN here is the line current, isn't it, class?
Yeah.
So if you take the magnitude IAN or I line, they're one and the same, and divide it by square root of 3, that'll reduce the magnitude, and then add 30 degrees to it. Only this angle now is what? That's going to be the angle of the source, right? And if you look at that, the angle of the source, our source here, was 0 degrees, right? For the A phase. Sorry. Boy, I'm not liking this. Do y'all see that the angle here is 0 degrees, 208, 0 degrees? So the current, right? Sorry, I said, you're going to add 30 degrees to IAN, and IAN was, I didn't calculate it right here. Can anybody give me that information, or am I going to do it? Let me put it right here. Can somebody give that to me? Magnitude and angle of this. It's in the solutions, I'm sure. Jessica, if somebody's looking, just tell me.
It's 11 with an angle of minus 52.09.
Anybody confirm that?
I can. I did it in my
Thank you. Thank you. Now that current right there is the current that would be in a Y connected source, but our source is delta. So to get IAB, and I'll put it right here, IAB would be this divided by square root of 3. And then the angle, you would add 30 degrees to it. Now, if I add 30 to minus 50 and add 30 to it, I get minus 22.09 degrees, right? Y'all follow me down that? Yay?
Yeah.
All right. You can check the answers later. That's the technique you use to do these. Got to say one other thing about this, right? The big problem is the square root of 3 all the time. So I'm going to recommend you do at least 4 or 5 problems. There's a bunch more in there. And make sure, without looking at the solutions, that you can go through those and effortlessly get the correct answer. Do you hear me? Recognize when loads are in parallel. The only loading you'll ever see on a power system will be in parallel. They'll never put in series. The reason they don't is if there's a failure or something severed and power is not used by one source because a line goes down, then the second source couldn't use it either. How many know what Christmas lights are? You're in America. If you don't know what Christmas lights are, you're probably dead. But anyway, if you know what Christmas lights are, you know that some are in series. When you pull one of the series ones out, the whole light fixture goes down, right? If they're in parallel connected, it doesn't matter. You can pull the bulbs and all that. I'm just making that analogy. That's why we don't have connections in series. There's more than that, but that's one of the major reasons. Good with that? Now, I wanted to get to those 2 examples. Now, I'll take questions from anybody about anything, transients, who knows what. Somebody's going to ask me how many problems on it. Well, I haven't made it up. It's likely 4 problems. I'm going to say it again, probably like 99.8% chance, 4 problems, equally weighted with multiple parts. Here's the idea. Take my quizzes, add 4 together. There you go. Well, what quizzes are you talking about? All my quizzes. I mean, most of the quizzes early on, the content and techniques you learn are actually embedded in the problems we do now. All right. You good with that? You're going to have to know current division, voltage division. You'll have to know power, all that. Can somebody tell me what's in chat, please? I see that it turns, an orange square turns on, and I don't know. They don't show me the chat one. Anything worth talking about or no?
No, I was just saying I was sorry for misreading it, wasting class time.
Oh, I don't care about that. Everybody makes mistakes, and I am the most sinful of all making mistakes because I make them using your time. So if anybody should be criticized, it's me. All right, what about other questions? Surely you have something. If you want me to, I'll just start throwing stuff out there.
Is the stuff from today on the exam?
Well, yes, because it was the homework on Monday, right? So sure. I'm not giving you any new material today. I'm just reviewing the old, is what this whole lecture is about. So I know some professors do, but at this point with Zoom especially, I feel just making sure you're settled here. If you've done this stuff and you feel confident, then you're in good shape. I'm just warning you about the common mistakes. Another common mistake I'm going to say, just because I see it, if people haven't been doing the homework regularly, you will find yourself struggling to remember, well, is it the current in the inductor or is it the current in the capacitor we solve? They're going to have fundamental questions. Please, any questions like that, make sure you answer to yourself so you don't have those. It's always voltage on a capacitor you're after, then anything else, right? Always current in it for transient problems, current in inductor, then in whatever else the circuit wants, right? We haven't done those in a while. When we're talking about Thevenin, the standard thing is what? We might as well do a quick Thevenin problem, if you're all right with that.
I would be, yeah.
All right, now I'm going to make one up. Suppose I want the Thevenin equivalent circuit for this and then the solution. I'm going to say I have a resistor here of 10 ohms. I have a capacitor here, minus J 6 ohms. I have an inductor here, J 5 ohms, right? And then I have a resistor here, I call it R load of 20 ohms. And I have a source. And I'll make this 100 volts at 0 degrees and make this peak, not RMS, okay? And what I want is the voltage here. All right, using Thevenin's theorem. Got me on that? I'm going to give you a second to write it down. Make sure you can see this and you're, oh gosh, I'm over. Class, if people need to go, please go. No matter what I do, it seems I run a little bit over, and I personally apologize to anybody who has something to do. If you need to go, go. This is a review. You don't need to be here for this, but if you are, good. And this should be available. If anybody has trouble seeing videos, accessing anything, let me know. OneNote or anything else, okay? Just to take a second break, since the class is technically over. And this is more for me than you. Is there any information about any closures downtown for bars, restaurants, or other things? Or any new developments in classes, class modalities? Because there's a whole lot of faculty that are concerned about having to teach in person next semester. And I, for one, welcome it. I welcome it with open arms, but there's people that don't want it. They're terrified. So have you heard anything about any of that? This is all COVID related, and it's for the benefit of you as well as me. Nothing? Nothing at all. How about you guys in the military? I mean, aren't you guys doing extra, having more precautions? No? No ROTC people with masks on or anything like that? You can't schedule classes this year? Or you can't do any early admittance or any early enrollment? No? I'm just wondering if you're hearing anything or getting any email. I'm not. Okay. Well, I'm saying that because I was a past chair of the University Senate, and a lot of people are complaining that And they think there's going to be a terrible amount of flu and COVID will resurface. I hope not. There's people in here, a whole bunch of guys and some women that have had COVID, and I'm very sorry you had to suffer through it, but I think everybody's okay. And if anybody is in the hospital, you know, please let me know. If anybody needs help, please let me know, and I'll try to arrange something. And I'm sorry I wasn't more outspoken about that. Okay, now for this one, we're done with our little break. First thing you do is what? If you're talking about using Thevenin's theorem for this.
On our load,
Well, yeah, what is it? You're right.
20.
Yeah.
No, sometimes you don't give it to us, so.
Well, that's 20 ohms. Agreed? Thank
Yeah.
you. What's the next thing?
VOC.
Well, we remove it. That's really, you're ahead of me, right? You remove it. Correct, class?
Yes.
Okay. So I'm going to redraw this real quick. You don't have to. So I got 100 volts, and then I have 10 ohms, right? Then I have minus J6. This kind of problem usually trips up a bunch of people because they're not thinking. In the past, I've seen. Now this is plus to minus V open circuit, right? Can y'all see this?
Yep.
How much current flows through that J5?
0.
How much voltage is across J5?
No.
0. No current across the J5, no voltage across it. Therefore, the voltage across this capacitor, I put the plus minus, is VOC. Do you agree with that?
Yes.
Now, I gave you a quiz that asked fundamentally that, and a lot of people got it wrong because they thought I have to use that for something. I'm noticing in this particular class, a lot of people believe if there's information, it must be used. That's not necessarily the case, or not every step. Please don't get into that mentality. All right, so really I want this voltage. What's the best way to get this voltage? Which is this voltage?
Voltage division.
Yeah, voltage division. It's just 100. I didn't put a phase angle on there for a reason. Then it would be over times minus J6 over 10 minus J6. Do you agree with me, everyone?
Yes.
I'll slow down. I see a lot of people writing, and that's good. Remember, more people turn on their cameras, the better it is for me. Hopefully, the better it is for you. And I know a lot of people have a lot of things going on besides this, but it doesn't matter. I'm leveling with you. Are you good with this? Now, next thing is, and we'll get this magnitude and angle. If you want to give that to me in a second, fine. The next thing is I redraw the circuit, right? Well, actually, what am I going to get? I'm going to get Z Thevenin, right? You agree with that, class?
Yeah.
Mm-hmm.
And what's the fundamental thing we have to do for Z Thevenin? We're looking at the impedance this way, right? That's what we're looking at. But we do one thing that's very important in this circuit. What do we do?
Turn resistors, or turn voltage sources into shorts, and turn voltage or current sources into opens.
Yes, we turn off the sources. That's the way I say it. Short voltages sources, open current sources. That's a voltage source. It gets shorted. Do you agree with that?
Yes.
Yes.
I'm just going to write it down. Therefore, Z Thevenin here would be J5, right? Right there. And then it would be plus the parallel combination of 10 in parallel with minus J6. I'm just going to write it down like that. Do you agree with that?
Yeah.
Yes.
I mean, nod, thumbs up, anything. And you know, you can turn on your mics because I don't mind if you're going to yell at me. Really, I don't. This is an office hour, and I have students in my office sometimes getting a little squabbles, and it's kind of funny. You all right with that, everyone? Now, once we have this, what else do we need to do? There's one fundamental thing now we have to do is assemble this final circuit to calculate what's asked for, correct?
Mm-hmm.
Agreed?
Yeah.
So we put the voltage source, which is VOC. And if you're looking at other references, some call this V Thevenin. They'll call it V Thevenin. It doesn't matter what you call it. It's the effective source of this final circuit. You put it here. So this is going to be plus the minus VOC, which is this value we'll get to. Then you put Z Thevenin here, right? Then you reattach the load. So the load looks like, I'm going to reattach it here. And that load was simply 20 ohms, right?
Yes.
Now, I'm going to ask for several things. First thing I'm going to ask for is the voltage across that. Remember, this is going to be a peak voltage across it, right? How many people are left, by the way? I can't see it on mine.
29.
29.
Might be an all-time record. So what will it be? VL would be,
Negative VOC.
well, VL would be, this is the voltage, it would be VOC, right? Times what? It's voltage division, it's what I'm going to use. You agree with that? It's going to be VOC, that's the source voltage, divided by, or multiplied by 20, right? That's the load, over 20 plus ZL. You agree with me?
Yes.
Everybody good with this here? I know it seems,
Yeah.
probably seems trivial. Trust me, a problem like this will cause massive, massive problems for people that haven't reviewed. Some of you laugh, but it's true. Now, I didn't fill in what VOC was. I didn't put Z Thevenin in here, and I didn't put that information in. But you obviously should be able to get this fairly straightforward. You agree with me there?
Yes.
And if
Yeah.
anybody wants to give me it, it's fine. It doesn't matter, but this is really what I want. So what is VL at the final end of the day? What did somebody get for VL? Let's see how many people get the same answer. See, this is kind of a test question. I mean, I could see myself asking that. Somebody say, how much will it cost to get that on the test?
The exam will be 50 minutes long, correct?
Yes,
Perfect.
it's a 50-minute exam, but some people get extra time. So, and I want to tell you one other thing. Please come early. If at all possible, please show up early. There is no external you can't use your phones, you can't use any kind of wearable electronics or any other device outside of your calculator. And that's the only thing you can use. You can't have any external information. You can't sit on solutions manuals or your phone. And I've had kids do stuff. I've had both of those things. One kid got almost kicked out of school. I really am encouraging you, just be on your honor system. If you do your work, you won't have a problem with this. This is not like an entrance to some elite society.
Would the voltage for the load be negative since the terminals are flipped? Like,
What do you, how are you saying they're flipped? This is plus to minus, right? Plus.
yeah.
How are you saying they're flipped?
Oh, I was just looking at how it's like at the same as the source. I don't know. I was just getting confused based on like, okay, JK, I just figured out my own question. Ignore that.
It's all right. It's better that people ask questions, and believe me, I'll say a lot of stupid things too, regrettably, but I'm sorry I do. It's human nature to make mistakes, and now's the time to make them, not during the test. Anybody? Magnitude and angle for the final answer. Let's see. You got a couple of different steps. What are you guys doing?
I got 45.42 volts at an angle of negative 60.53 degrees.
Say that angle again, sir.
Negative 60.53.
Anybody else? Confirm or deny? Hey, use your calculators now. You think I'm kidding? Just entry of data and recovery of data from your calculator is a big deal. There are people that will mess this up just with simple 2x2 matrices. I'm not kidding you. Complex matrices drive people nuts sometimes. How many
Yeah,
got?
I got
I got-
30.
Go ahead.
I got 33.8 at an angle of negative 68.5.
33.8? That doesn't look like it's the same.
Yeah. I got the same thing Joseph got.
All right. Now, I don't know if this is the right answer. I'm kind of betting it is for a different reason. Because the values I chose, I think would bring that about. But again, I'm not absolutely sure. But you see with this problem, if I give you this problem by itself, you keep working that problem. If you haven't done it, I want to see how many people get the same answer. If you look at this problem, and I just throw this out to you, I'm going to level with you. Thevenin is probably the easiest way to do it. Now, if you want to do it with loop analysis, you can. You'll get the matrix equation. Do you all agree with that? If you want to do a loop, you're going to get a matrix. You can do it that way. If you want to put nodal here, put a node here and ground it, you're going to get a node voltage, and then you're going to use voltage division to get this voltage. You can do it that way. But in my personal opinion, Thevenin is the easiest. Now, I'm saying this to you. Thevenin, unless you're told to use something else, is probably the easiest. Are you with me? I'm trying to help you. And by the way, those of you who are in mechanical and aero and any other engineering that's going to be using any kind of large systems with multiple devices plugged into the same ports, think about finding a Thevenin equivalent for everything. Keep seeing something here. You got 45? Okay. All right. I'm going to go with that answer. You good with it? Everybody? Are you okay? All right. Now, the other thing I'd like to review, unless does somebody have any other burning issue you want me to go over?
So just to make sure, that is 10 minus 6, 10
What?
minus J6 when you're calculating VOC
What,
on the denominator.
well, yeah, but I mean, what am I doing? I'm ignoring this entirely, right? I'm just looking at the voltage across here, correct?
Yeah.
All right, well, that voltage here would be the source voltage, 100 times this impedance minus J6 over the source, or the sum of these two, which would be 10 minus J6, right?
Yes.
So that's what we got here, right?
Yeah. I was just wondering if that might be why the two different answers, because that minus kind of looks like a plus.
What is a plus?
10
That's a
minus.
plus? This is
I'm
got
just
to be
saying it
10.
kind of looks like one, so that might be where the different answers are coming
No,
from.
that should be minus part. It's this plus this. I'm sorry.
I know. When I plugged it in, I used a minus in that particular place.
This is a minus.
I know.
Okay.
I'm just saying that I went back and corrected myself. I had put a plus in there.
Oh, okay.
So I was wondering if other people made that same mistake.
They probably did. They're never going to admit it, though. Well, maybe they'll admit. I try to admit my mistakes. Oh, they're painful to admit, but it's the reality of being a human being. You'll make them. And the more you work at this, the fewer you make. All right. Now, any other people got burning issues about this? Okay, how about a transient problem? You good with that? Okay. Unless somebody's got something else for me. For transient problems, boy, I don't know which one's more common. Let me actually see if we got a really wild one in here. Dave Irwin's book, sometimes he has a day where he says, we'll give him something. They'll mess this thing up sideways. No. All right, this isn't bad. How about we talk about it for a second? How about we do 340?
All right.
All right, now when you look at this one, I know you've done this before, but just listen to me. Before you just whack away at a problem and start writing equations, stand back and look at it for a second. I got one source and I'm looking for this voltage. Okay, I want this voltage, got one source, and it's an inductor resistor problem, not a capacitor. Therefore, the thing I need is the current through that inductor. Y'all agree with me there? I need the current through the inductor, but I have to, to really get this thing off the ground, I have to define a direction. So I'm going to call this the direction of current, and I need that current for t greater than 0. Can you all see this?
Yeah.
Now, I'm going to try something. Now, if you see that right here, now just listen. Don't do anything. I can see I have 3 and 3. I have 3 ohms and 3 ohms. Do you all see they're in series?
Mhm.
I want to make
Yeah.
sure you do. I mean, if you possibly can turn on your screens and give me some affirmation from those that are here. I appreciate the 3 people that have it, but it helps me immensely. The more heads that are actually alive, and some people, Jessica, I don't know what's going on, but thank you for your thumb. That's good enough. If I see this, I'll make that 6 ohms. Do you all see that? I have 6 ohms. Do you all see it's in parallel with 3? Can you
Yeah.
all see that? So if I have 6 in parallel with 3, isn't that 2? Right? 6 times 3 is 18. 6 plus 3 is 9. 9 into 18 is 2. So it's 2 ohms. That whole thing right there is 2 ohms. Just start with that, reducing. Next is that 6-volt source. It's DC 6 volts. You could draw it at the battery. Now I look over here, go for t less than 0 first. There's a switch there, and it's open. Over here I have an inductor. What does an inductor look like when it's been in the same state for a very long time? It's one word, or 2 actually.
Short.
Short circuit. It's a wire, right? It's a wire if nothing's happening, so replace it by a wire. Now, that is the current I want, and this would be for t less than 0, correct, class? And then I have what? 2 ohms in front of it. So when I look at this, if I want this current, I, through the inductor for t less than 0, that's going to be 6 volts, right? And 6 volts is pushing current this way divided by 4 ohms, or it would be 3 by 2 of an amp. Do you all agree with that? That's the first thing. Take a good look. That's this problem. You all get this for the current for t less than 0.
Yeah.
All right. If possible, for all the people that are still dwelling here, can you let me, someday I hope you get to experience what I am. It looks like there's a whole host of people, but only a few are responding. It doesn't matter. Okay, now I have that. Now when the switch closes, what happens? Take a look at this. This is the circuit still, right? Only there would be an inductor here. When this switch closes right here, what happens when it closes here? In your own words.
Parallel.
When this closes, what does it effectively do to this part of the circuit?
Cuts it off.
It's completely cut off from the source, right? This point becomes ground, doesn't it, when that switch closes, right? That means there's no source to sustain current through that inductor. Do we all agree with that?
Yes.
And therefore, current must go to what?
0.
ILT goes to infinity is 0. That's the second thing. Correct, class?
Yes.
Giving people time to write it down. Now, go back to this circuit and look again. And again, I appreciate people who turn their cameras on. It makes my life so much easier. All right, now, the next thing I want to do is what happens, or what do we need to get next? We need to get the Thevenin equivalent impedance or resistance, whatever you want to call it, across the inductor after it's removed, right? Y'all agree with that?
Yeah.
Now look, after it's removed for t greater than 0, when t is greater than 0 and I look at this, right, that switch is closed. So really what I have is this. If this switch is closed, Here's where the inductor was. And there's a closed switch. It's coming back here, and there's 2 ohms. Do you see how R Thevenin is 2 ohms? Take a look, everybody. Thank you. Thank you. You guys got it?
Yes.
All right. Now, after we have this, and the order is not important. It really isn't. But that you do this. Now, the next thing I get after I get that is going to be tau. Tau for an inductor is L over R, right? L is 1, R is 2, therefore it's 1/2 second, right? You agree with me? I mean, y'all agree that tau is L over R for an RC or RL circuit? Blech.
Yep.
Okay. Now, we get the equation, we put it in the final form. I know that therefore IL of t is equal to K1 e to the minus t over tau plus K2. But what is K2 actually? Isn't that the current as t goes to infinity, class?
Yeah.
Right? It's the current as t goes to infinity. And what is the current as t goes to infinity for that circuit?
0.
It's 0. So we don't even use that, do we? Now, therefore, that's the current through the inductor. And what would K1 be? Just by looking at it.
3/2.
Yeah, it'd be the current at t equals t less than 0, right? Or 3/2. So now I have IL is of t equals 3/2 e to the minus t over 1/2 or 2t. And it's really for t greater than or equal to 0. Y'all got me on that? I'm just restating what I talked about. Now, come over here to this, and if you got that current for t greater than 0, that's what we have, right? Then what's the voltage going to be? It's as obvious as it seems. It would be that current that we just calculated times 2. How many see that? Now, I know I did it. It looks simple. Something that simple on the exam will cause some people, unfortunately, to really have trouble. To me, it's obvious if you do several problems and you know what you're doing, you should feel very comfortable in that environment. I'd like to do one with a capacitor. Does anybody have a suggestion for a capacitance problem?
Real quick before we move on, I guess I'm still slightly confused as to why when the switch closes that it completely cuts off the rest of the circuit.
Okay. Let me ask you this. If I have a battery, I hope you can see this.
I can.
Just make it 12 volts. And I have a resistor 2 ohms. Then I have a switch right here. And then I have another resistor here, 2 ohms. And I want to know the current through there for t greater than 0 if this switch closes at t equals 0. I just want the current through there. What is it and why? Well, when this switch closes, right, doesn't it effectively do this, right?
Yeah, because the current's going to go to the passive least resistance.
All the current goes there, and there's no voltage across here. If 0 volts divided by 2 ohms is 0 current, if you want to think of it that way.
Okay. All right.
Believe me, there's no silly, dumb questions here. And if you ever run into people that ridicule you for asking that, get away from them. They're dangerous. They'll make you be fearful of asking about things you don't understand. It's a horrible thing when you see that. Okay, everybody good with that problem? Now, does anybody have a capacitor problem for me?
3.25 or 3.29.
Let's find the hardest one. 2.29.
The capacitor ones with switches were all homework 10.
Yeah, I want. Is there a hard one? Really hard. The harder, the better. I think 33 would be even better than that. Take a look at 33.
I agree.
33 is really, this is right out of the pit. But actually, it's quite easy. You'll be able to do it. Now, I take a lot of, I'm very satisfied with most of the students that I teach that overall, when they get through this course, they'll have absolutely no problems with the fundamentals of engineering exam, electrical part of it. If, I'm saying if they try. It pleases me that that happens. So I'm going to take 33. Let me try to do it this way. I'll probably get a nasty letter for inking up this book. How can you do that to a book? Or an email or something like this. I get all sorts of anonymous messages about how horrible I am for doing things to books. Well, I haven't got too many of those lately, but a lot of stuff comes my way. Some of it is tongue in cheek, but some of it is serious. So for this problem, let's look at it together before we do anything. Can you all see 33? And if you have the old homework, just look at it. And you know, I advise everybody, print out your old homework. Can you all see this okay? Now, look,
Yeah.
for this one, let's first take a look at this and talk our way through it. They want this current through the 6K resistor. The solutions manual may actually do a solution in terms of that. Don't ever do that. The thing we want is the voltage across the capacitor. Do you hear me?
Okay.
Do it the way I say, you won't mess up. We're after the voltage across the capacitor. Here, the switch is open for t less than 0. We want the voltage across the capacitor. Again, we want that for t less than 0, t greater than, t goes to infinity, and then we want R Thevenin across it, right? That's the goal. Now, hear me on this one. So if I look at that, that switch is open. What does that capacitor look like when the switch is open? Forever.
Short circuit.
Open, right? Capacitor, think of what a capacitor is. It's two pieces of metal with a dielectric, right? Right? A dielectric, if there's nothing changing with time, there's no current flowing through it. It's like the insulation on an extension cord is basically a capacitor. If you take an extension cord, don't plug it in, and you measure across it, the dielectric would be the insulator between them. There's no current at all unless there's time changing voltage. Now, that being the case, it's an open circuit, so it looks like this. I have 36 here. I'm just trying to write this quickly. 36. Then I have 2K. Then I have the open, I'm going to call this plus to minus VC here. That's the capacitor. Then I have 6K and 4K, and the switch is open, so I'm going to not even draw it, which would be 10K, right? 10K, and then I have a voltage source of 12 volts. Y'all agree with that?
Yeah.
Kind of a rotten redraw. If I want this voltage, my opinion is this. The easiest way to do it is just find the current and then find the voltage across that 10K and add it to the 12. You give me that, people?
You say that again? I was looking
Sure.
at-
How about if I add this and this together, which is 12K. That's the series resistance in the circuit. Then I look at these voltages. I got 36 volts trying to shove current clockwise, 12 volts to shove it counterclockwise. 36 minus 12 would be 24. So the equivalent to get this current would just be 24 volts, right? And then it would have simply 12K. And that would be allowing me to calculate I. Do you agree with that, people?
Yeah.
Okay. Therefore, what is I? It would be 12 over, or it'd be 24 over 12K. Or it would be 2 milliamps. Do you agree with that?
And can you do that anytime voltages are in parallel?
They're not in parallel, they're in series.
Or yeah, series, my bad.
Series, sure.
Yeah.
How much is it trying to, you know, how much voltage is trying to shove things around? They have to be in series. It has to be a single loop. How much voltage is trying to push it this way? 36. How much is trying to push it this way, the current? 12. 36 minus 12 is 24. That's as simple as that. You good with that? So I have 24 and I have 12K resisting it. Therefore, my current is 2 milliamps that will be flowing. when I go back to this circuit, if I have 2 milliamps, right? That means this voltage, it's flowing into, would be 2 milliamps times 10K, or it would be plus to minus 20 volts, right? You all see that?
Yeah.
Okay, you good with it? I mean, you see it, right? If you're doing something else at the same time, not a problem, but if you can give me a little affirmation, it helps. Anything at all. And I appreciate your cameras. Thank you very much for those who have your cameras on. Now, if I've got that voltage here, what is the voltage minus the plus? It would be what? Increase of 12 and then an increase of 20 or 32 volts, isn't it, class? So my voltage across the capacitor for T less than 0 would be 32 volts. You good with that?
Yes.
Thank you. Everybody?
Not quite.
What do you need?
So where are you getting the 32 from?
Okay, do you agree this is 20 volts here?
Yes.
And you agree this is 12?
Okay.
So I'd start the negative terminal, increase of 12, then increase of 20 would be 32. Everybody good with that? And can you all see what I've got here on my screen? When I see people squinting, it makes me concerned. You good with that? If you're doing this on your iPhone or something like that, a real small device, I'd recommend you try on a larger screen. But you know, some of you have great eyes and I don't. Are you good, everybody? All right, now once I have that, the next thing I need is the voltage as T goes to infinity, usually, right? Let's re-examine this circuit. Here, this is 33, right? Now take a look. When this switch closes, what happens? Well, doesn't this part of the circuit get taken out? That's a short from here to here, right?
The forums and the 12 volts you're talking about?
Yeah, because that goes from here to here is a short. So I have 6K directly across that capacitor and 2K in series with it, right?
Mm-hmm.
Let me redraw that for you. I'm going to redraw above. So for T greater than 0, and actually goes to infinity, I'd like to say, but we'll just do greater than 0 for now. I have the 36, and I have the 2K.
You just had a frame.
Mm-hmm. Oh, yeah. Then I have the capacitor, which is 100 microfarad. And I have 6K in parallel with it. That's K ohms. Now the rest of the circuit doesn't matter, and the reason being is when that switch closes right here, it shorts this out and it removes these two as being an issue. Is everybody okay with that?
Yeah.
Now, when I look at this, first I want the voltage across this capacitor as T goes to infinity, right? Well, we got VC for T goes to 0. What would VC be as T goes to infinity by looking at this? Take a look. What does this look like as T goes to infinity? What does the capacitor look like, class?
Open circuit.
Yes, because there's nothing changing with time, right? Nothing changing with time. No current can flow. It's effectively an open circuit. So what's this voltage going to be? Well, it's just like it's not there, right? And we're looking for the voltage across that 6K, correct, class?
Yeah.
What's that voltage going to be, anybody?
We'll do voltage division.
Absolutely. 36, right? I'm going to say it. 36 times 6 over 6 plus 2, or 36 times 6 divided by 8, right? Or 36 times 3 divided by 4. I'll write it down. So this would be 36 times 3 divided by 4, right? Oh, 4 into 36. Is that 9? Anybody there?
Yeah, it's 9.
Isn't that 9 times, and then what it would be? 9 times 3 would be 27, correct, class?
Yeah.
So this would be 27 volts. You all agree with that? I'm going to make it mandatory next time I have to
Yeah.
use Zoom in a classroom setting that everybody has their cameras on or they'll lose like 2 points a lecture. Something, because this is irritating the heck out of me. I don't know if you're there or not. Anyway, look, it's office hours. I'm going to office hour talk my real thoughts. All right, I got a voltage T equals 0. Voltage T goes to infinity. What else do I need?
T greater than 0.
We got, no, well, yeah,
Here.
but what do we really need anyway?
Tau.
Yeah, but what do we need to get tau? You're right. There's one essential thing.
The Thevenin resistance.
Yeah, thank you. So now I need the Thevenin equivalent resistance when that capacitor is removed, right?
Yes.
What's that going to be? What do we do with this source, first of all? Class?
Turn it into a short.
Short.
We short it, right? When that's shorted, what do we have? Isn't the 2K in parallel with the 6K? Can y'all hear me? When this shorts, doesn't this have 2K in parallel with 6K across that capacitor?
Yep.
And what would R Thevenin be then? I got this voltage, I got voltage. Therefore, R Thevenin becomes 2 in parallel with 6, right? Would be 2 times 6 over 2 plus 6 or 8. So it's 12 over 8 or what? Divide both by 4, I get 3, right? Halves.
3/2, yeah.
Agreed? And then that's R Thevenin and it would be in K ohms, right?
Yeah, off the screen.
Thank you. It would be in K ohms. Is that right, class?
Yes.
Now, if I have that in K ohms, the next thing I need is tau. Remember, it's an RC circuit. I hope you can see this. So what would tau be?
R times C.
Thevenin times C. Yeah, it's R Thevenin, right? So here we have 3/2 times C. What was C in this one again? That
100
was
micro.
100 microfarad. That's 100 times 10 to the minus 4th. I mean, 10, it is 10 to the minus 4th, so 100 times 10 to the minus 6. So that's really 1.5 times 10 to the minus 4th seconds. You agree with it?
Wait. So where does the K? So it's K ohms.
Oh, I'm sorry, times, you are so right. This is times 10 to the 3rd. So it's going to be 3/2 times 10 to the minus 4th times, because I forgot the K, times 10 to the 3rd. And that would be what? 1.5 times 10 to the minus 1 or 0.15 seconds. Thank you very much. And that would be tau. Now that we have that, what do we do? I've got the voltage T less than 0. Voltage T goes to infinity. I've got tau. Now I'm going to back to this one. But you're getting a little fatigued too. Now I go back here and I say, therefore, I know the voltage across the capacitor as a function of T is K1 e to the minus T over tau plus K2. Right, and that's not the circuit, but you all with me, correct, class?
Yeah.
Mm-hmm.
We want this. We know VC for T less than 0 was equal to 32 volts. We know VC for T goes to infinity is equal to 27, right? And then we know tau is equal to 0.15 seconds, right? Now we put the whole thing together. I know that K2 is the voltage as T equal infinity. Do you all agree with that? I'll let everybody get their bearings. And I appreciate everybody here. I do, and I appreciate you turning on your cameras. Thank you, Joseph, John, Gabrielle, and I think there were a few others earlier. Thank you very much. So do you all agree that K2 would be equal to the voltages T equal infinity? Agreed?
Mm.
Yeah.
Yes.
Not so much. I kind of don't agree. If you don't agree, can you give me a kind of reason for it? Okay, I'm going to take it you agree mostly. If you don't, tell me. I mean, you all see when time goes to infinity, this term goes to zero because of that exponential, right? E to the minus infinity is 0. Agreed? So I know K2 is this voltage. I've got this voltage. Next, I need K1. I solve for K1 at T equals 0. So at T equals or 0 minus equals 0 plus here, and I can say that this is 0 equals K1, right? Plus K2, which is 27, but that's not the case. What is the voltage for T less than 0? It's 32, right? Here's what I see, though. I'll see a 0 right there. I don't know. I mean, that's just kind of one of these knee-jerk. It's 32 volts is the voltage for T less than 0. The voltage is T equal infinity is 27. At the connection point, T equals 0 minus 0 plus, we equate this to the voltage at T less than or equal to 0, which happens to be 32. And we solve for K1. And you can see K1 is what? 5, right? Agree?
Mm-hmm.
Everybody?
You lost me.
All right. If 32 equals K1 plus 27, K1 has to be 5.
Yeah.
Okay. That's my own point. Now, if I have this, I can restate that. I can say that VC of T is equal to K1, 5 e to the minus T over tau, 0.15.
You're out of frame again.
Thank you. 0.15. This is VC plus 27. That's the voltage across the capacitor. Now I'm going to, y'all agree with that part?
Yes.
Okay. John, can you see this okay too? All right, everybody. Now, if I have that, now I bring back the problem, which is here. If I take a look at this, I have this voltage, don't I? Agree? That voltage is across all this stuff. Now, this is already shorted out. So really for T greater than 0, it's across here as if that 6K was down there, connected there, right? So I've got the voltage, right, across the 6K, don't I? I want you to take a look. If that voltage is across the 6K, this 36 and 2K have nothing to do with the actual current through that capacitor for T greater than 0. You all see this. This part has no bearing. This is 36 volts and 2K because the voltage across the 6K is the voltage across the capacitor that we've got. How many see that?
Okay.
Kind of. Well, what don't you see, John? You see, when this thing switches and closes, you see how that point is that point? If that point is that point, can't I take that 6K and just bend it and connect it here if I want? All right, isn't that in parallel with the...
I see what you're saying now.
All right. If you see that, then you know the voltage across that capacitor is the voltage across that 6K period. And if I wanted the current through the 6K, I would just take the voltage across the capacitor by 6K. You all see it?
Yeah.
No,
What don't you see, Joseph?
I just don't see it. I don't, like,
Well,
how is it?
You agree that switch brings this point electrically to this point when it closes for T greater than 0.
Yes.
You'll see that 6K, I could take that and redraw it and put a 6K right there, right?
Yes.
Isn't that 6K in parallel with the capacitor?
Okay. Yeah, I see it now.
And therefore, if I have the voltage across that 6K, I have the current through it. I just divide it by 6K. That is my point. And therefore, the current that they want for that problem, I sub 6K of T is simply equal to this VC of T divided by 6K, or it's equal to 5 over 6K e to the, now let me do it this way. E to the minus T over 0.15 plus 27. And that's it. You good with that?
Yeah.
That was a tougher problem than who picked that last problem up? Is he still here? I know it's a guy. I just don't know who it was. Was it you, Thomas, or not?
Maybe. As
The capacitor problem, did you throw one out there 330?
yeah, but this one ended up being just as difficult, if not harder.
I mean, this is harder because it's got a final voltage, but this is the kind of problem you're going to get in the test. You're going to get something where there's a final state probably that's non-zero. That's the reason I did this.
Okay.
I call it harder. It's not really harder. It's just more steps because it requires you to solve for a non-zero value of voltage. T goes to infinity. Okay.
Going back to the Thevenin resistance,
Yeah.
I'm slightly confused as to why 2 and 6 were in parallel versus not in series.
Okay, help me out here. For this problem?
Yes. So when we were calculating the Thevenin resistance.
Thevenin equivalent resistance, right?
Yes. Sorry.
That's for the capacitor, right?
Yes.
All right, now look, for the capacitor, the points that we're calculating, we remove the capacitor and calculate the Thevenin equivalent resistance where that capacitor was, right?
Yeah.
All right, remove it in your mind and short that. This 2K goes to ground, right?
Yeah.
That 6K goes to ground, right?
Okay.
Aren't both of those in parallel?
Yes.
That's the
what?
reason.
Yeah. So we're shorting the capacitor there.
No. We remove it. You literally rip it out of the circuit. This is what's left. It would look like, here's where the capacitor was. There's where I want our Thevenin. Over here, I have 2K going to ground. And then over here, I have 6K going to ground.
Perfect. Okay.
That's
That makes
what happens.
sense.
Please, go ahead.
I need to redraw it more. That's what I'm figuring out.
I'm going to level with you. There is no value you can put that's high enough on making sure you can do these problems basically effortlessly. If you struggle with these problems, come test it. Because I've gone over the solutions and you have the solutions, man. You'll have probably a major problem on a test. You have to feel very at home with this stuff. It shouldn't be one of these things where you just wince every time you see it. Okay. I wish I could say something to give you more advice, but I've done it. I've told you already, you can't do enough problems really. And work problems, I'd say for 50 minutes, take a break, 5-10 minutes, come back 50 minutes again, then take a good half-hour break, 20 minutes to a half hour. After that, come back and do the same thing again. You can work a long time doing it and you'll be surprised how much more efficiency and how much more you get done. The time will vary for some. Some people can work, they can work literally 115 minutes in a row before they need a break. But all people hit a point where you start fatiguing and making mistakes. That's where you need the break to refresh. It'll help you. If you're just bludgeoning through these things and you hate them, you're not going to do, it's not the best way. It's the least effective way. You will not retain it either, unfortunately. So now I've done those two things. As far as circuit analysis, we're using circuit analysis for everything. So that means Thevenin, Thevenin, mesh and nodal. We're using everything that we've talked about. Power, we know the relationship between DC and RMS, right? So what else are you going to give me a question? I'm really looking for a question from you. I've done what I thought is valuable to you. I mean, the problems. Anybody?
Go through loop or mesh analysis. I can't remember which one, but I missed a lecture on one of them a while ago and I never went back to rewatch it.
Loop and mesh are the same.
Okay. I figured they were.
It's just summing the voltages, mesh is summing the voltage. They're the same thing.
Yeah. But like I either had a test in another class that went over into your class, I can't remember, but I missed the whole lecture on it.
Let me give you one piece of advice. If you look online for problems, there's a cajillion problems with circuit analysis. I mean, with solutions. Some of you have access to solution on that Chegg thing, whatever it's called. There's all sorts of stuff out there. You can, I recommend you make sure first and foremost that you can do any problems that I assign easily. That's my first recommendation. The homework problems and any problems that extra problems that I didn't assign that are part of the homework stuff that I've given you the answers. Second, you're going to look for external sources. Beware of getting things too difficult. Now, MIT has a lot of free course stuff. I recommend that place. Other places, I'm not sure. There's things out there that'll probably confuse you more than help you. Now, it's 2:45. I got a few things to do now, but I've given this the best shot. So I got to make out that test next. Are you good? Any final thoughts from anyone?
Do you see us using superposition or source transformation all that much on the exam?
I never went over superposition, I don't think. Source transforms are effectively Thevenin Norton or Thevenin equivalents, but you can, yes, source transforms can make problems easy if you feel.
Yeah.
That's fine. I mean, I show you stuff that I use that's beneficial. I don't just show you stuff for showing it. Superposition, I don't think anybody uses it.
Okay.
Maybe they do. I'll probably get an email from somebody if the whole class is here. It's amazed at how many emails I get per day from this class. It is astonishingly large. And it's varied topics. I mean, all over the place.
That's a good thing.
It's good to hear from you. Some of it hurts. Your writing couldn't be any worse. I don't believe you. Anyway, I try.
I've started uploading all of the Zoom recordings to YouTube.
Thank you.
It takes forever, so I'm only about a third of the way through.
Well, I don't know what to tell you there.
One of the early Zoom recordings you left running for 8 hours.
Oh my God.
I thought, well, I'll just put it up to YouTube and use their editor, but their editor doesn't let you edit videos, like trim videos over 4 hours.
Look,
and you had looked like a pretty personal discussion with a student, like with medical records. I was like, I don't want to upload that one to YouTube.
Don't. Matter of fact, sometimes I say stuff I wish I wouldn't, but I try to really help you guys. I've sat in your chair and like this isn't EE circuits. EE circuits is a little more challenging. As a matter of fact, a lot more challenging in some cases. But when I sat where you were, the thing I wanted was a professor that tried to put himself in my position so he could best answer the questions I had. Some professors don't. I mean, they are way above you, and frankly, they got better things to do than talk to you. And I don't think that's the best thing for students. But I'm really trying. Has anybody ever seen Paper Chase? No. Paper Chase is a movie about two students in Harvard Law, and they got the hardest professor named Kingston at Harvard. And Kingston could care less if they fail. It's really interesting. At least that's his end.
Wait, is that the movie where it's like two burnouts like try to steal the test answers and they have a heist?
No. These two guys they literally for the examination they get a hotel room, and the guy tries to get him out of the hotel room, and they basically make him think they'll bust him for the drugs he's bringing in if they try. To me, it's pretty funny. It's filled with humor that's really not going to happen, but it's an interesting view of professor-student relationships. Look, guys, I wish you the best. You got questions, hit me up or Chun-Li, and please come early. Please get you enough sleep. If you want to bring a drink, please do. No food. I mean, if you want to bring a candy bar, as long as it doesn't make noise, fine. But no, like potato chips or things that go crunch. Don't bring a Big Mac in there. Things like that, okay? I'm trying to be as fair about this. I bring coffee all the time. I used to teach. And if students want to, or whatever your beverage. Okay?
Well, if you want to put yourself in my position, this is going to be my third test this week.
Oh
So,
God, this week.
yeah,
You've
I
taken
had a
two
test on
already?
Tuesday. I got one tomorrow, and then yours is on Friday.
Well, the one thing I'll tell you is what time's your test?
Tomorrow it's going to be at 2.
I will tell you this. Study for this some. All right. What class?
Statistical quality design and control.
Is this in math or is it in IE?
It's INSY course.
I don't know what it's required. If you've been keeping up, then after that, I would take a break, take a nap, whatever, and get up. And I would not stay up real late. But by now, you've probably done most of your study. Most people should be keeping up with this. So the day before and stuff like this. The real issue is this. They're just reviewing. There's little bits that they see that they're going to, but people that are cramming, there's the ones that are going to get, especially on the final, they get hurt bad. I'll just tell you one thing, get your rest. That will help you more than any cramming will, really. I don't know if anybody knows this from personal experience, but every single person I know that does stuff after, like consistently after the courses, keeping up with the homework and all, they usually don't have any trouble. When they cram, for whatever reason, they regret it. Unless it's a course like art history or something. You can get away with it there. When you have to analytically think, you're going to regret it, I think. So that's my advice. You look kind of tired. Maybe you need a nap now.
I was planning on taking a nap after this.
I encourage naps. Thomas Edison lived on naps. He only got about 4 hours of sleep